Okay, guys, Mass 6500, kind of shooting from the hip on this one, so hopefully this goes okay. If it find out it's not going for okay, then you'll never know because I'll scrap the video. Like it seems like we do quite a few times throughout a semester, and put it up later. I looked at this stuff a couple of days ago, but I think I'm okay with it. Let's think. I'll tell you what. Let me back up here. What we want to do, or what I want to do with you, is in this video is to examine two other situations that may arise when looking at regression coefficients. And it turns out that these two other situations, we have to use what's called the general f-test. Now, I don't know if it's clear yet, the difference in the general f-test and the partial f-test that we've been exploring lately with this extra sum of squares. When I say general f-test, I want you to think back to what we did in 5500 before this whole notation of looking at a model and then exploring the effect of adding a couple or one or two or three, whatever it may be, coefficients or variables to it. General f-test, just think further. Just think about the standard ANOVA for regression that I introduced you to in 5500. So general, guys, not the partial that we've talked about so far. Now, the second thing I want to do after we examine a couple of other situations is I want to get into the general f-test a little more. Now, this is back when I was teaching 1500. Whether or not to explore the general f-test was something I had to kind of get over. It probably would have been best to look at it back then, but I skipped over it, thinking that you guys were going to have a year between 5500 and 6500, most likely. You never know the way the schedule's going to fall out. But so anyway, I made an executive decision to wait and look at the general, at least the kind of the development of the general f-test in this class. So now that you know all of that, let's just assume that we've got a 3 predictor model. So we should know by now that it would look like beta 0 plus beta 1 xi1 plus beta 2 xi2 plus, that should be a plus, not a, plus beta 3 xi3 plus the error term, okay? Now, let's consider a couple situations. What if we wanted to test whether, for example, beta 1 is equal to beta 2? That might be something we may want to test, and we want to test it over the obvious alternative hypothesis. Well, the way that we would carry this out is we would let beta c be the common beta, if you will. So in essence, beta 1 will equal to beta 2, which will equal beta c. It's what the value that these two things are equal to. The way the procedure carries out is we let y sub I equal beta 0 plus beta c, which is taking the place of beta 1 and beta 2. So we're going to add xi1 plus xi2. And I think possibly there's a something on your assignment that requires this, but I may be wrong. I'm not. And then the rest of the model is just the remainder of the full model. Okay. Well, if we want to test this, we use f star, which follows the f distribution, which will have degrees of freedom 1 and n minus 4 for obvious reasons in the 3 predictor model. And again, that 4 comes from the fact that we have 3 predictors plus we have an estimate on beta 0. The 1, the way I think of this, is we're creating an extra measure, BC, the combined beta, so that's kind of where that degree of freedom comes from. Guys, if we're doing this, we must use the general F-test. Okay. Another situation that we could run into, let's say we want to test that beta 1 is equal to some number and beta 2 is equal to some number. Let's say 1 and 2. Well, the alternative, as you should know by now, is at least 1 of the statements in H sub O is not true. So not, both equalities or quantities, if you will, in the null hypothesis hold true. Now, the reduced model in this case in this situation would be yi equal beta 0 plus, forget what I said over here, 1 beta I 1 plus 2 beta I2. Oh, Doug, come on. Daggone it. Losing my mind here. At least we're assuming that. Well, I'm glad I caught that. That would have been horrible. Plus 3xi3 plus the error term. So, again, all I did is put in the values that we're actually testing. Now, we would rewrite this in this way, just bringing the hypothesized values over with the y. And it turns out that this test statistic would follow the F distribution degrees of freedom 2, I think for obvious reasons, and n minus 4 still because we have beta 0, beta 1, beta 2, and beta 3. All right. Let's go to the, let's take a look at the general F-test. Again, what should you think? What we saw in 5500, none of the fancy stuff. Although we're going to kind of use some of the extra sum of squares notation here. So let's consider, and what I want to look at is I want to look at this in the simple linear regression case. So in the simple linear regression case, or the simple linear regression model, it's probably more appropriate to say, we have a full model just as you would expect, okay? And we would fit this model using one of two ways. We could use maximum likelihood estimation, and we could use least squares. And guys, obviously, one way down the list, we could use R. Okay, but mathematically, we could fit this using one of these two techniques, which is exactly what R would do. Now, one of the important measures that we take a look at in this simple linear regression case is the sum of squares for the error. So the sum of squares for the error for the full model is just going to be the sum from I equal 1 to n of y sub I minus beta 0 plus beta 1 xi squared, which upon investigation you can see that this is just the sum from I equal 1 to n of y sub I minus y hat sub I squared. And guys, this is nothing more than the sum of squares for the error. So at the end of the day, the sum of squares for the error, or the error sum of squares, measures the variability which is just kind of thinking about measuring the spread of the y sub I observations around the fitted regression model. So gang, if we have a set of points, hope you guys can see this, like that, it would be reasonable to think that the fitted regression line would kind of go down through the central focus. This situation would have a smaller sum of squares than if we had this situation. So this is, again, measuring the kind of average variability around the regression line. And that's something, you know, we've seen quite a bit there. Now, what we would look at next is, let's consider what, I don't know what I want to do next. Okay, let me just pose this question. What would the reduced model look like? Well, considering that there's only one predictor in the full model, it should be, again, following kind of the patterns that we set up so far. We're going to test guys, this is obviously an A right there. We're going to test beta 1 equals 0 versus beta 1 not equal to 0. So if H sub O is true, and I got to put that in parentheses because that's not the purpose of a test of hypothesis. So we might say or confirmed, supported. Then what happens? And if that's supported, that's confirmed. We say that beta 1 is equal to 0, so we get the reduced model. And what's the reduced model going to look like? Just the model without the beta 1. If the slope is equal to 0, at least if everything points toward the slope being equal to 0, then there's no need to include beta 1 in our model. And guys, obviously, my pen's wearing out. I have one of these, well, I don't even know what you call it, like a donut or a donut. I have no idea, but they have these kind of plastic ends, and when they get kind of worn down, which mine's getting worn down a lot here lately because I've been teaching so much online. They don't write as well, so it looks like I'm in dire need of upgrading. Now let's think this through. If we fit the reduced model, see how that skips there, and you should know me by now enough that drives me crazy. But anyway, if we fit the reduced model, just like for the full model using maximum likelihood estimation or method of least squares, then the sum of squares for the error, or the error sum of squares, for the reduced model will look like what? Well, we're saying that the slope is equal to 0. So there's no linear trend. And if we think about this as being a minimum on y, and think about this as being a maximum on y, and about through here somewhere is going to be the mean for y, then it would make a lot of sense that the mean for y is going to be our B0, our line of best fit. We certainly wouldn't want that to consider that as the line of best fit, because again, we want our line to go down through the central focus of our data. So gang, because of that, we can say that the sum of square error for the reduced model will be the sum from I equal 1 to n let me be consistent with what I don't even, let me go back. I want to check something out here. Okay, yeah. All right, so this is going to be beta 0 squared. And if beta 0 is just the mean, it should be clear from what I did, over here. Then we have y sub I minus y bar squared, which is precisely the sum of squares total. Did you know that? If you didn't, tell me you did, just so it makes me feel good. So guys, the logical next step is to compare the sum of squares, or the error sum of squares for our full model with our error sum of squares for our reduced model. And for obvious reasons, we should know that the sum of squares for the full model is either going to be less than or equal to the sum of squares for the error model. Now, if the sum of squares, the error sum of squares for the full model is equal to the sum of squares, error sum of squares for the reduced model, then the addition of beta 1 was completely irrelevant. But you would expect this inequality to hold true. Now, the reason being is the more predictors that you have in the model, the better you should be able to fit the data because you should have smaller deviations around the mean. But anyway, I think that doesn't need a lot. This right here doesn't need a lot more explanation because it's pretty clear. Now, if let's just say the sum of squares, the error sum of squares for the full model is I hate these words, but I don't really know how else to put it. Slightly less than is very vague, but let's just say that we know what that means, and the sum of squares, the error sum of squares for the full is just slightly less than the sum of squares error sum squares for the reduced model. Well, if this is the case, this is support for H sub O. If there's not much difference between the error sum squares for the full model and the error sum squares for the reduced model, then at the end of the day, why put beta 1 in there if the goal is to create the model with the least number of predictors? However, let's say that the error sum of squares for the full model is a lot less than the error sum of squares for the reduced model. And this indicates that the addition of the parameter beta 1 produces a substantial reduction in the sum of squares, the error sum of squares for the full model. And in this situation, it should be pretty clear that there is a lot of support for H sub A. That the slope is not equal to 0. So by including beta 1 in our model, the variation of y around the fitted regression line is substantially reduced. So guys, in the simple linear regression case, we obviously would test this set of hypotheses. And typically, what are we testing? Well, typically we're testing the alternative. And we should know that the sum of squares for the error for the full model, which is just the sum of squares, the error sum of squares, has degrees of freedom n minus 2. And again, y the 2. Beta 0, beta 1, right? And the sum of squares, error sum of squares for the reduced model is just the sum of squares for the total, which we should know is just n minus 1. Guys, the F statistic is equal to, again, I like to present stuff like this when I'm teaching. So we're going to have n minus 1 minus n minus 2 for obvious reasons, because we're going to look at the sum of squares total minus the sum of squares regression. You probably see where I'm headed with that, over this error sum of squares, which has n minus 2. Well, boys and girls, you should know by now that this reduces to the sum of squares for regression over the degree of freedom 1 over the sum of squares for error over degrees of freedom n minus 2, which leads us to the mean square regression over the mean square error for calculating our F statistic. So this F statistic is going to follow the F distribution with degrees of freedom 1 n minus 2 for obvious reasons. So we could easily calculate the p-value using R for this method. Guys, that's all I got. This is going to come in really handy for your next assignments. So that's it. Have a good one.